Hello, dear friends. Wishing you all the best, blessings and happiness of Nag Panchami festival, mostly celebrating in Maharashtra and some remaining region in India. Today is the last lecture as long as rotational dynamics is concerned. That is the lecture number 20. And in this lecture, we want to study total kinetic energy of rolling motion, then linear velocity of rolling motion and acceleration of rolling motion. That means we want to derive three physical quantities, that is total kinetic energy, linear velocity and linear acceleration of rolling motion. So before proceeding further, my humble request to all of you that observe my all lectures from rotational dynamics 1 to 20 very carefully, very sincerely. Make your own notes. Most of you have subscribed me and given comment time to time to make me more energetic. So remaining all of you, please subscribe my channel. Name of my channel is Physics Make It Simple by Dr.Rajendra and remain continue with me to enjoy, to learn physics in the channel Physics Make It Simple. Okay. Before chit-chatting else, we will continue the main article. The article is that I have already written on the board. The article is what? Total kinetic energy, linear velocity and acceleration of rolling motion. That we want to learn now. For that purpose, I have drawn a diagram of inclined plane like this, and I have put a rolling body at top of the inclined plane, which is at a distance h, and this inclined plane is making an angle theta with the horizontal, and whatever labeling is required that I have already written. Suppose v is the linear speed of center of mass of this sphere, because this center of mass have linear speed. When it roll down like this, when it roll down from top to bottom, at that time it has two types of motion. The first one is that rotational motion as well as translational motion. So rotational kinetic energy plus translational kinetic energy, we get kinetic energy of rolling body or rolling motion. That is most important thing. R is suppose radius of a body, omega is angular velocity, capital M is suppose mass of the body, and we know capital K is nothing but what? Radius of gyration of the body. So by making use of this triangle, I will have to find sine theta at first. The value of sine theta we got is h upon s, because this is a rectangular triangle and sine theta is equal to front side upon diagonal of the triangle, that is s. So we get sine theta is equal to h upon s, and from this calculate the value of s. S is a displacement of body from top to bottom. When the body is rolling like this, the body is rolling like this from top to bottom, at that time rolling body have displacement s, which is given by h upon sine theta. That's all. So initially I have already told you that we have to calculate the value of total kinetic energy of rolling body. So total kinetic energy of rolling body is a combination of what? Translational kinetic energy plus rotational kinetic energy, because this is a rotational kinetic energy, and as long as during rotation body is transferred linearly from top to bottom. So there are two types of kinetic energy translational plus kinetic energy rotational. Summation of these two, we get total kinetic energy of rolling body. Okay. then total kinetic energy of rolling body or motion, which is equal to, we know translational kinetic energy is given by the formula 1/2 mv square, where v is the linear velocity, capital M is the mass of a body, plus rotational kinetic energy. We have already derived the formula in this chapter. The rotational kinetic energy is given by 1/2 I omega square. So in this way we got equation number 1, that is total kinetic energy of rolling motion is equal to 1/2 mv square plus 1/2 I omega square. This is equation 1. So put the value of capital I in terms of radius of gyration. Capital I is equal to mk square. We know V is equal to R omega. From that, what is the value of omega? Omega is equal to V upon R. In equation 1, put omega is equal to V upon R. Here square, we get V square upon R square. Put the value of I is equal to mk square, like this. So we get total kinetic energy of rolling motion or rolling body, which is equal to 1/2 mv square, this term remain as it is, plus 1/2, put the value of capital I. What is the value of capital I? Which is equal to mk square. What is the value of omega? Omega is equal to V upon R. So square, V square upon R square. What common we take? 1/2 mv square. We get common, into bracket 1 plus 1/2 mv square remain common, k square upon R square. So this is the total kinetic energy of rolling body or rolling motion. Remember well, total kinetic energy of rolling motion, which is equal to 1/2 mv square into bracket 1 plus k square upon R square, where k is radius of gyration of the body and capital R is radius of the rolling body. So after completion of the total kinetic energy, we want to calculate linear velocity V of rolling motion. So how we can calculate linear velocity? To calculate linear velocity, we have to make use of law of conservation of energy. What is law of conservation of energy is here. When the body is at rest at top, body has its potential energy. Body has its potential energy. Full of potential energy is present in the body because body is at rest. So what is the potential energy when the body is at rest? Initial velocity u is equal to 0. Body is not rolling. Initially the body is at rest. At that time body has its potential energy because it is at rest, and initial velocity u is equal to 0. So potential energy we get is mgh. Capital M is mass of a body, g is acceleration due to gravity, and h is height of the inclined plane. That is potential energy. Pe is equal to mgh. Initial velocity u is equal to 0. Okay. So this is the case that I have written here. Using law of conservation of energy, potential energy is equal to total kinetic energy of rolling body. As long as the body starts moving, body starts rolling from top to bottom, potential energy starts converting into rolling kinetic energy. I will repeat again. When the body starts rolling from top to bottom like this, making a displacement yes, at that time potential energy starts converting into rolling kinetic energy. And because of having such a statement, I have written here, dear student, potential energy is equal to total kinetic energy of rolling body. So we know potential energy, that I have already told you that potential energy is equal to mgh, and total kinetic energy of rolling body that we have calculated here, which is equal to 1/2 mv square into bracket 1 plus k square upon R square. So put here 1 half mv square into bracket 1 plus k square upon r square. So these two values we'll have to put in equation 3 here. We get what? Potential energy mgh is equal to total kinetic energy 1 half mv square into bracket 1 plus k square upon r square. So here what happens? This capital M and capital M get cancelled and take a v square on LHS. V square is equal to remaining part is 2gh upon 1 plus k square upon r square, and square root of v square we got is v is equal to square root of 2gh upon into bracket 1 plus k square upon r square. This is equation 4. So in this way we have calculated linear velocity of rolling motion. To calculate linear velocity of rolling motion, dear student, remember well, I will repeat again, we have to use law of conservation of energy. When the body is raised at top, at that time body has full of its potential energy, and that potential energy is equal to mgh, which start converting into rolling kinetic energy when it starts rolling from top to bottom, making a displacement s. In this way we calculate by making use of law of conservation of energy. We get linear velocity of rolling motion v is equal to square root of 2gh upon into bracket 1 plus k square upon r square. Okay, then we have to calculate linear acceleration. What is linear acceleration of rolling motion? To calculate linear acceleration, remember our kinematical equation. What is our kinematical equation? Kinematical equation we know is that I have written on the board, v square is equal to u square plus twice as, where a is a linear acceleration and s is a displacement of rolling body. When it moves, when it rolls from top to bottom, the displacement of body became s, that is displacement. We know that I have already told you that initial velocity u is equal to 0. When the body is at top, body is at rest. So u is equal to 0. What is the value of displacement s? The value of displacement s that we have calculated here by making use of such a triangle, and we get s is equal to h upon sin theta, that we have calculated early near the diagram. S is equal to h upon sin theta. So s is equal to h upon sin theta. What is the value of v square? We know v square is equal to this 2gh upon 1 plus k square upon r square. So from equation 4, v square is equal to 2gh upon 1 plus k square upon r square. U is equal to 0 and s is equal to h upon sin theta. These three values we'll have to put in equation 5. We get this. Put the value of v square here. U is equal to 0 plus 2a. What is the value of s? H upon sin theta. And solving this, these 2 get cancelled with these 2, and we get acceleration is equal to g sin theta. This h is cancelled with this h. This 2 is cancelled with this 2. G sin theta. This sin theta goes up. G sin theta upon 1 plus k square upon r square. Equation number 6. This is a linear acceleration of rolling body. And remember well, dear student, in this way we have derived 3 formulae. Number 1, kinetic energy of rolling motion. Kinetic energy of rolling motion we got is 1 half mv square into bracket 1 plus k square upon r square. Then linear velocity of rolling motion, that value we got is v is equal to square root of 2gh upon 1 plus k square upon r square. Then after that you have calculated what? Linear acceleration. The value of linear acceleration a is equal to g sin theta upon 1 plus k square upon r square. So in this way we have calculated 3 values. As long as this article is concerned, we have to remember 2 remarks that I have written on the board. The first remark is that for a rolling body, if I will write capital I is equal to small n mr square, then that small n, the value of small n will be k square upon r square. When we put I is equal to small n mr square, then n is equal to k square upon r square. Okay. Then I have taken one example. Suppose the moment of inertia of a rigid sphere, solid sphere. We know moment of inertia of a solid sphere is capital I is equal to 2 by 5 mr square. 2 by 5 mr square. By comparing these two equations, it clearly indicates that value of small n is equal to k square upon r square, and k square upon r square is equal to what? 2 by 5, because small n is equal to 2 by 5 and n is equal to k square upon r square. From this it clearly indicates that then for a sphere k square upon r square is equal to 2 by 5. When the value of k square upon r square is equal to 2 by 5, then the body is solid sphere, like this. This is most important thing, and this formula we should remember always for solving the various types of numericals. That formula is for rolling body, the ratio translational kinetic energy as to rotational kinetic energy as to total kinetic energy is equal to 1 as to k square upon r square as to into bracket 1 plus k square upon r square. This formula we should remember for the various numericals, to solve various numericals. We should know these two formulae, that is when capital I is equal to n mr square, then n is equal to k square upon r square, and this is the formula, that is translational kinetic energy as to rotational kinetic energy as to total kinetic energy is equal to 1 as to k square upon r square as to 1 plus k square upon r square. Dear students, in this way we have successfully finished rotational dynamics. Give me such a type of continuous response to make this physics more simple, because our channel name is Physics Make It Simple by Dr. Rajendra. Okay, we will proceed further by taking next chapter in the next lecture. Okay, we will stop here.